Hello, my name is Jorge Cortez. I am a principal solutions architect at Aviatrix, and previous to that, I was an Azure Networking Global Black Belt, where I helped hundreds of customers architect their networks in Azure, following Azure best practices and cloud adoption framework. I am pleased to talk about networking in Azure as part of this ACE Associate training. So let's get started. Resources in Azure are organized in a well-defined hierarchy. The topmost level is the Azure AD tenant. It represents an organization and its users, and it is the identity service used across all Microsoft cloud-based offerings like Microsoft 365. With an AD tenant, users can be given permissions to create Azure subscriptions. There are different subscription types users can sign up for depending on the billing model. It is within these subscriptions that, depending on the user's permissions, they can create different resources from the entire Azure portfolio of services, including networking services. Every resource must be created under a resource group. A resource group is a management boundary for the resources contained within. This allows organizations, business units within an organization, or departments within a business unit to delegate management of resources to the teams and/or users responsible for the services the business delivers, as well as perform cost tracking. Each resource within a resource group must have a unique name, and each resource group within an Azure subscription must have a unique name as well. But resources in different resource groups and resource groups in different subscriptions can have the same name. There is another level in the hierarchy called a management group. This was introduced to allow organizations enforce a consistent governance strategy by grouping multiple subscriptions under a management group and applying a set of policies at the management group level, rather than having to do it individually for each subscription. Depending on the user permissions, it is possible to browse the entire portfolio of Azure services through the Azure portal. This can be done all services at once in a single pane or by service category. When navigating into a service, depending on the user's permissions, it is possible to create a new resource for that service, browse existing resources for the service, or perform a number of management operations on existing resources for the service. A resource is an instance of a service, and it must belong to a single resource group in a single subscription. Azure offers close to 200 different services, and they are grouped in over 20 different categories. Some of the most relevant categories are compute, where services like virtual machines, web apps, and Azure Virtual Desktop reside. Then under the storage category, we can find services like blob storage, disk storage, and Azure NetApp files, to name a few. Under networking, we have virtual networks, DNS, we have VPN and express route gateways, content delivery network. Then under databases, we have Azure SQL DB, which is a relational database, Azure Cosmos DB, which is an object database, and Azure Cache for Redis. Under containers, we can find services like Azure Kubernetes Services and Azure Red Hat OpenShift. We also have container registry, container instances. Under identity category, we have Azure Active Directory, which again, it's the identity store used across all Microsoft cloud offerings. Then under security, we have services like Microsoft Defender for Cloud, which is a cloud workload protection platform and a cloud security posture manager. We also have Azure Sentinel, which is a SIEM and a SOAR system. We have Azure Firewall. We have Web Application Firewall. There are also artificial intelligence and machine learning services offered. Some of these services are Azure Databricks and Azure Cognitive Services. Note this is not an extensive list of the categories and services. If you want to consult all of the services Azure offers, you always can refer to the Azure official documentation. Azure Core Networking Services. To begin with, we have Azure Virtual Networks. They provide seamless connectivity and a data plane boundary for resources deployed within them. This is why a virtual network is sometimes referred as a virtual data center. It's important to note that only resources in the same subscription as the VNet can be deployed in a virtual network. Resources cannot be deployed in a VNet though. They are deployed to one or multiple subnets within the VNet. Note, however, that unlike on-premises networking, where routing between subnets must explicitly be configured, routing between subnets inside a virtual network in Azure is implicitly configured, and all services deployed in a virtual network can communicate among themselves by default. Just like on-premises networking, subnets need to be allocated a CIDR range or an address prefix. This range must be a subset of the range or ranges allocated to the virtual network. It is important to note that the smallest CIDR range that can be allocated to a subnet, and hence to a VNet, because a VNet must have at least one subnet, is /29. The reason for this is because Azure reserves the first 3 addresses of a subnet, in addition to the network and broadcast addresses, which cannot be used by host. So Azure ends up taking 5 addresses, and allocating a /29 subnet leaves us with only 3 addresses to be used by hosts. Although a VNet supports multiple CIDRs, and those CIDRs can be as small as /8, a VNet only supports up to 65,536 host IP addresses. So this is very important when planning for IP addressing space on Azure in order to avoid wasting valuable IP blocks. The next construct in Azure is a network interface card. This is the construct or object that actually provides all the networking services to virtual machines. This is abstracted when creating a virtual machine through the Azure portal, meaning that it is automatically created when a virtual machine is created by the portal. However, when creating virtual machines in a programmatic way, either through PowerShell or REST API, Terraform, artifacts, or ARM templates, network interface cards must be explicitly defined as objects. Depending on the virtual machine size, a virtual machine can support up to 8 network interface cards, and all network interface cards associated with a VM must belong to the same virtual network, although they can belong to different subnets, but they cannot belong to different virtual networks. Each network interface card supports up to 250 public IP addresses and 250 private IP addresses. And this is important to keep in mind because, again, a virtual network supports up to 65,536 IP addresses total. Additionally, Azure provides a DNS service by default for all resources deployed inside a virtual network. This service automatically resolves DNS queries for public names. In addition to that, VMs in the same VNet belong to the same internal DNS zone by default, which allows VMs to communicate among themselves using their hostnames. This internal DNS service can be overridden by configuring custom DNS servers in a VNet. Note, however, that when using custom DNS servers, these must either be virtual machines deployed in the same virtual network running a DNS service, and this can be Linux bind servers or Windows Active Directory servers running the DNS service, or they must be servers deployed on premises, but virtual machines inside a VNet must have a way to communicate with these DNS servers for it to work. In addition to the internal DNS services, Azure offers both a public and a private DNS service where users can manage their own DNS zones and records. So public DNS servers are announced records to the internet hierarchy. So you must own your domain name for that. And private DNS zones are only for resources deployed in the VNet. They can also be used for resources used on premises, but Azure DNS service doesn't offer a forwarding service. So you need to deploy a virtual machine to provide this DNS forwarding service in order to provide DNS forwarding between on-premises and Azure. Now, if users need to allow access to their virtual machines from the internet, they can create a public IP addresses, and they can associate these public IP addresses with network interfaces or other constructs like load balancers or Azure Application Gateway. Note, however, that users cannot choose the actual IP address they want to use. Even if they choose a static type public IP address, you still cannot specify the actual value of the IP address. Instead, Microsoft assigns an IP address from the pool allocated to the region where that IP address object is created. The difference between a static and dynamic public IP address is that static public IP address, once the IP address is allocated from Microsoft, it won't change value. Whether a dynamic IP address, if you stop or deallocate the virtual machine that has that IP address associated, the next time you start it, that IP address will change. One important thing to note, public IP addresses are only required for inbound internet connectivity. Unlike AWS, for example, all virtual machines have outbound internet connectivity by default, regardless of whether they have a public IP address or not. This is just the design of Azure. Now, moving on, we have the Azure Networking Routing Services. As the name implies, this provide routing between the different constructs in Azure. The first construct or object that we have here are route tables. In many cases, the default flat routing behavior provided by virtual networks, remember that within a virtual network called subnets can talk to each other by default. Sometimes this is not desirable and more complex routing scenarios are needed. Route tables provide a way for users to configure up to 400 static routes in a subnet. Only a single route table can be assigned per subnet, and a single route table supports up to 400 static routes. This can be useful when, for example, internet-bound traffic or inter-subnet traffic must be inspected by a firewall. The challenge with the static routing, of course, is that it puts a management burden on users because now each route must be individually maintained and configured. It's no different than when you have static routing on premises on your routers. Those are static entries. If they change, you need to go in those devices and update those route entries manually. A single route to a destination can exist in a route table. And this can be a challenge for redundancy purposes, right? If you have two firewalls, well, you can only have one route for the remote network, and it can point to one or the other firewall. And there are strategies in Azure like load balancers for that redundancy, but the point is only one route per destination can exist. And of course, each route can have a single next hop. It's because of this limitation that Azure recently announced Azure Route Server. This service provides a way for any capable device to dynamically exchange routes with Azure Fabric.
And what do we mean by Azure Fabric? It is the software-defined network stack responsible for providing networking services to Azure deployments.
It can pair with up to 8 VP speakers, and each speaker can advertise up to 1,000 routes via VP. So pretty much Azure Route Server, it's a VP speaker device and pairs via VP with network virtual appliances that are capable. Now, when multiple speakers advertise the same network prefix to Azure Route Server, meaning they have the same VP path attributes, Azure Fabric will perform equal cost multi-pathing. And by the way, Azure Route Server only uses AS path length to compare routes. Doesn't use weight, it doesn't use local preference. So pretty much two routes that have the same AS path length that are advertised to Azure Route Server, they are considered equal. And it also supports AS path loose, meaning the first AS in the AS path doesn't have to be the same. Azure Route Server only looks at the length of the AS path. It doesn't care if the first AS in the AS path is the same or different. If they have the same AS path length, they are considered equal cost routes. And Azure will perform equal cost multi-pathing among those routes. It supports up to 8 equal cost routes. That's the limit. It's a hard limit, cannot be increased. And of course, this equal cost multi-pathing is great for devices that don't keep any sort of state. They are just plain routing devices like virtual routers, right? Like Cisco vRouter or Arista VEOs or Juniper VSRX, or SD-WAN solutions that all they do is they move packets from one side to the other. However, this behavior of doing equal cost multi-pathing, it's a problem when dealing with devices that keep state. And by that, I mean functions like firewalls or devices that do a stateful NAT, which require that both flows in a communication go through the same device. Otherwise, it will break the traffic. And the reason for that is because when we are doing equal cost multi-pathing, there is no guarantee that the return flow will be sent to the same device that processes the inbound flow. So we run into an asymmetric routing scenario. And for devices that keep state, this will cause connectivity problems. Hence, when using firewalls in high availability active-active scenario, it is still required to use static routes in UDRs, as we mentioned earlier, just to make sure that the traffic is always kept symmetrical. There's also a need for hybrid connectivity most of the time between the deployments in Azure Virtual Network and deployments that reside on premises. And this hybrid connectivity is achieved with the use of virtual network gateways. There are two types of gateways depending on the type of connectivity desired. If the connectivity over the public internet is enough, then we can use the virtual network gateway. This gateway does connectivity using a standard IPsec encryption. There's another construct called a local network gateway. It represents the on-premises device that's terminating the VPN tunnel from Azure. For virtual network gateways, VPN gateways, both policy-based traffic selectors and route-based tunnels are supported. Route-based tunnels support either static routes, or they can also support BGP, so we can have BGP over IPsec. When using BGP over IPsec, there's a limit of 4,000 network prefixes that can be learned across all IPsec tunnels. Azure has documented some throughput limit, tunnel limits for these gateways based on the gateway size, the largest of which supports up to 100 IPsec tunnels and 10 gigabits per second. And again, this is aggregate throughput, which means all of the tunnels created cannot exceed 10 gigabits per second. However, each IPsec tunnel is still limited to a maximum throughput of 2 gigabits per second. And again, this is on a perfect day when the sun is shining hard. And this can only be possible when using GCM ciphers. Most IPsec implementations, especially legacy, use CVC ciphers. With CVC ciphers, actually you are limited to up to 700 megabits per second. And again, those 700 megabits per second are on a perfect day when the planets have aligned and the sun is shining really hard, right? Now, if connectivity over a dedicated connection is desired rather than over the internet, then we can use an express route gateway and an express route circuit. So those are two components like the virtual network gateway and local network gateway. Here we have an express route gateway and a circuit. An express route gateway can achieve up to 10 gigabits per second aggregate throughput, and it can be connected up to 16 express route circuits, depending on the size of the express route gateway that you choose and the on-ramp location for these circuits. It can actually only connect to 4 express route circuits in the same on-ramp location, but you can have up to 16 circuits across different on-ramp locations. Now, an express route circuit can provide up to 10 gigabits per second when the service is contracted through a service provider partner from Azure, like Equinix, AT&T, CenturyLink, or it can provide up to 200 gigabits per second when a model called ExpressRoute Direct is used. And what ExpressRoute Direct is, it's pretty much a direct link between the customer routers, the routers that you have on premises, and the Microsoft Edge routers. And in order for this to be possible, customers need to rack and stack routers at a co-location facility where Microsoft have Edge routers, and then they also have to run the fibers from that location to their premises. There are two circuit SKUs. One is a standard and one is premium. The difference is a standard circuit supports up to 4,000 VP prefixes, pretty much the same as with the VPN gateway from on-premises, and can be connected up to 10 different ExpressRoute gateways. This is regardless of the size of the circuit and the gateway. Premium circuits, they support up to 10,000 VP prefixes from on-premises and can be connected up to 100 different ExpressRoute gateways. But this number is dependent on the circuit SKU, the smallest being 50 megabits per second and the largest being 10 gigabits per second in the case of a provider circuit, or 200 gigabits per second as we discussed for ExpressRoute Direct. However, regardless of the SKU, an ExpressRoute circuit supports up to 1,000 network prefixes being advertised from Azure. So what does this mean? Remember that virtual network can have multiple CIDR ranges. Each CIDR range associated with a virtual network is a network prefix advertised down ExpressRoute. We can have up to 1,000 different, and this might sound like a lot for a single VNet. However, for scale scenarios, when you start having multiple VNets together, this can become a challenge. And the problem is, once you advertise 1,001 prefixes over ExpressRoute from Azure, then that ExpressRoute circuit will go down and it will cause an outage. Another thing to note is that these ExpressRoute gateways and VPN IPsec gateways, they are different resources. Unlike AWS, that you have a virtual gateway, which can be used for VPN and also for direct connect if you want. And only one of each type can be deployed in a VNet. So a VNet can have up to 2 gateways, a VPN gateway and an ExpressRoute gateway. When both of them are deployed in the virtual network and the same network prefixes are reachable over both of them, meaning we're advertising the same network prefix over ExpressRoute and over VPN, ExpressRoute will always take precedence over VPN from Azure to on-premises. What communication channel you use to send from on-premises to Azure, that depends on your routing policies. But from Azure to on-premises, it will always be over ExpressRoute, and this behavior cannot be overridden. There's no way that you can manipulate route attributes to make Azure send traffic over VPN rather than ExpressRoute when you advertise the same prefix on both channels. If you prefer to use VPN over ExpressRoute for some prefixes, the only way to do that is to advertise more specific prefixes over VPN and then over Azure. So Azure honors longest prefix match, meaning the route that has the most specific prefix will be used first. Additionally, it's important to know that Azure doesn't allow communication between remote sites connected by ExpressRoute and remote sites connected IPsec VPN by default. So if you have your virtual network and then you have both VPN gateway and an ExpressRoute circuit, and you have some branches connected via the VPN and your data center connected over ExpressRoute, those branches cannot talk to your data center through Azure. You need to have some communication between them, probably through an internet service provider or probably an MPLS network, but you cannot do it through Azure by default. However, it is possible to make this transit happen by deploying Azure Route Server and enabling branch-to-branch communication through Azure Route Server, and that will allow that bridge to happen. Another construct that we have is VNet peering, virtual network peering. This allows to interconnect multiple virtual networks together. Resources deployed into different VNets, they cannot communicate, they are isolated from each other. If we need that communication, then we can peer those two virtual networks. These virtual networks can be in the same or different regions. It doesn't matter. For different regions, we have global VNet peering. And when they are peered, all traffic remains within Microsoft managed network. Microsoft has a global network. They have fibers all around the world. So traffic never leaves Microsoft managed network into the internet. This connectivity of VNets, it's useful in a couple scenarios. When we don't have any more space to keep adding services to a VNet because of limitations, for example, the 65,000 IP addresses that are supported, or when business unit isolation is desired, meaning each business unit gets assigned its own virtual network to deploy their services. All those business units need to consume core services. Usually these core services are networking and security services like DNS servers or Active Directory servers. They have to be shared across all business units, and they are usually managed by the IT team, not by a business unit, but by an IT team of a company. In this scenario, you can put all of those shared services in a VNet called the Hub VNet, and then you can connect all the business unit VNets to this Hub VNet to VNet peering. It's important to keep in mind some limitations with VNet peering. I think the most notable are: one, VNet peering is a one-to-one, non-transitive relationships between peer VNets. So in the case of hub and spoke topology that we were mentioning, the business unit VNets that are peered to the hub VNet that has the common services, they can access all of the resources deployed in that hub VNet. They cannot talk to other business unit VNets that are peered to the hub, right? So that's one. The other one is all communication between services in different VNets that are peered. It flows unencrypted. It goes clear text. There's a limit to the number of VNet peerings that a VNet supports. Currently, that limit is 500 VNets. However, this might change in the future, so always refer to Microsoft documentation. Azure also offers a set of network security services to help customers protect their workloads at the network level. The basic security service offered by Azure is network security groups. This can be thought of like a network ACL in on-premises routers. Each network security group is an ordered list of rules based on priority. There's a limit of 1,000 rules per network security group that can be configured. Each one of these rules can either deny or allow traffic using the 5-tuple of source IP address, source port, destination IP address, destination port, and protocol. Only a single NSG can be applied at the subnet level, or it can be applied at the network interface card as well, or it can be applied at both. You can have a subnet level network security group and a network interface network security groups. When this happens, rules that have deny action will take precedence. So it's not that one is evaluated after the other. That's not the case. Rather, Azure will condense all of the rules applied at both levels into a single set of rules, and deny action will always take precedence. Now, there is another construct called application security groups. This construct is used to group network interface cards together, regardless of the subnet or IP address associated with it. As long as the network interface cards belong to the same virtual network, they can be grouped under the same application security group. And this application security group can be used as the source or destination in a network security group. So the idea with this is that instead of relying on a network identity, like an IP address or a port number, now we are relying on the application or service that that virtual machine provides, or that network interface provides. So it adds more context to the network security group. Also, if an IP address changes in this network interface card, the network interface card will still be part of that application security groups. So the rules that are referencing these application security groups will still be enforced. One more thing is that network security groups in Azure can only be used for TCP, UDP, and ICMP traffic. Other traffic is not supported, and also traffic like GRE is not supported in Azure. As a matter of fact, GRE traffic is dropped by Azure, regardless of DNSG. The other thing is deny rules in network security groups only impact new connections. Existing connections that have already been established. For example, if a virtual machine is compromised and it's already communicating with a C2C, a command and control server, you cannot configure an NSG to tear down that connection because it has already been established. So a network security group will only act on the TCP three-way handshake. UDP is stateless, so that's not a problem. But with TCP traffic, because it's stateful, it only acts upon the three-way handshake. They only impact new connections. In addition to the network security groups, Azure offers a centralized layer 3, layer 4 stateful firewall, which provides advanced capabilities like intrusion detection and prevention system functionalities. It also provides web browsing restriction based on web categories, fully qualified domain name filtering, and it also provides threat intelligence using Microsoft Security Graph. Now, because it is centralized, meaning it's an appliance, and it doesn't support integration with Azure Route Server for dynamic route advertisement, it means that when using Azure Firewall, we also need to use static routes, user-defined routes, to send traffic to the firewall. And remember, because these are static routes, they need to be manually configured and maintained. It's also important to know that Azure Firewall only supports TCP and UDP traffic. It doesn't have a web application firewall capability, so it cannot be used to protect your web workloads that are running HTTP, HTTPS, or WebSockets. For those workloads, the recommendation is to use Azure Web Application Firewall. This is not a standalone service. It's actually an add-on functionality, and it can be tied to Azure Application Gateway, Azure Front Door, and Azure Content Delivery Network. You need to have any of those in order to be able to use a web application firewall. It cannot be coupled with Azure Firewall. Azure Web Application Firewall can use the OWASP core rule set. It can also use custom rules based on different HTTP headers, or you can have the OWASP, which is the standard for open web security. When both are used, custom and OWASP rule core set are used, custom rules are evaluated first, and then OWASP rules are evaluated. Another security service that Azure offers is Azure Distributed Denial of Service Protection Plans. There are two types of DDoS protection. One is basic, and the other one is standard. The difference is basic, to begin with, it's enabled by default and it is for free. However, that service, DDoS Protection Basic, is only designed to protect the Azure infrastructure at large. It's not designed to protect your workloads from denial of service attacks. It's to safeguard the Azure infrastructure to avoid impacting a large number of customers. If you want to have protection for your specific workloads, again, denial of service attack, then this is when a standard protection plan is needed. Pretty much what DDoS standard does is it uses a machine learning algorithm to learn traffic patterns
destined
to resources with a public IP address that reside in a VNet that you have associated a DDoS standard plan with. And it will automatically block traffic that deviates from the learned traffic patterns. In addition to that, DDoS standard offers monitoring and visibility, as well as what they call rapid response support team. So if you are experiencing a DDoS attack, you can contact this group. If you have a standard protection plan, you can contact this group and they will help you with it. Then the last service within the security services category, it's actually 3 services, but they are all interdependent. It's private endpoint, private link, and private link services. These 3 services work in conjunction with each other. And the idea of this service is to allow clients for these services to connect to Azure PaaS and provider SaaS services over private network. If you work with Azure or many other clouds, the PaaS services, they are originally consumed over the internet. Like you consume them over a public IP address over the internet, but some highly regulated industries that need to consume these services, they want to consume these over a private network using a private IP address. And this is the reason these services were designed. Now, the distinction between private link and private link service, because this causes confusion, is that private link is to be used with Azure PaaS services. What does it mean? Azure SQL DB or Azure Cosmos that we looked at, those services that Azure provides, we can create a private link for them and then link it to a private endpoint, which represents a flexible network interface card for the service. And that's it, that's private link. Now, private link service can only be used with infrastructure as a service services, meaning if you are a service provider and you are offering to multiple clients service that you run on virtual machines, right? Like you design the service, the code, it's running on virtual machines. If those virtual machines are placed behind a standard load balancer, you can expose those services rather than over the internet. You can expose them into your customers' consumer VNets as with a private IP address using private link service and private endpoints. Azure also offers a set of load balancing services. The first one is a simple layer 3, layer 4 load balancer for TCP and UDP traffic. This load balancer can either be external with up to 600 public IP addresses associated to it, or it can be internal. The load balancer distributes traffic to the backends using a 5-tuple hash algorithm by default, consisting of source IP, source port, destination IP, destination port, and protocol. It can be changed to either a 3-tuple or 2-tuple hash algorithm, but other load balancing algorithms like round robin are not supported. It's important to note that Azure Load Balancer is not a reverse proxy. It only performs destination NAT for traffic
destined
to the backends and source NAT for return traffic from the backends. This allows it to preserve the client IP address. On the other hand, it doesn't support advanced features like TLS termination. We also have Application Gateway. This is an application delivery controller for web traffic. It supports HTTP, HTTPS, and WebSockets protocols. It can be deployed with a public IP address only for exposing web workloads to internet clients, or with a public and a private IP address for both internet and internal clients. Cannot be deployed with an internal IP address only, but traffic from internet clients can be restricted using network security groups. It acts as a reverse proxy. It terminates connections from clients and creates new connections to the backend servers. It supports advanced functionalities like TLS termination, end-to-end TLS, and HTTP headers rewrite. And the backends for an application gateway can either be in Azure or on the internet. Application gateway is a regional construct, meaning it can only exist in a single region and in a single VNet. Another application delivery controller for web traffic is Azure Frontdoor. And unlike Application Gateway, Azure Frontdoor is a global resource and not bound to a specific region. It leverages edge locations around the world along with Anycast routing to ingest traffic closest to the clients. And it also provides CDN functionalities and TCP connection acceleration. However, it doesn't support WebSockets. As with application gateways, the backends can be located in Azure or anywhere on the internet. Backends located in Azure can also be exposed to private endpoints, which removes the need to expose them to a public IP address. Now, if a global load balancer for non-web traffic is needed, Azure Traffic Manager is a DNS-based global load balancer. This service supports 6 different routing methods: priority for active standby deployments, weighted for canary deployments, performance for sending traffic to the backend closest to the client DNS resolvers, geographic to route clients depending on their DNS resolver geography to backends, multi-value, and subnet. However, it's important to know that being DNS-based doesn't sit in the data path, and it is tied to the client and client's DNS resolver behavior, which can lead to clients using stale DNS records, resulting in high convergence time. Finally, we have NAT gateway. This is not a load balancer. It is actually used to provide outbound internet access using a predictable and consistent IP address for all virtual machines deployed in a subnet without the need to allocate a public IP address for each virtual machine or using a public load balancer. NAT gateway provides 64,000 outbound ports per IP address allocated to it, and it supports up to 16 public IP addresses that can be associated with a NAT gateway. So now that we have taken a look at the different networking services offered by Azure, let's look at some architecture examples. The simplest architecture is having everything deployed to a single VNet. In this architecture, the VNet is created in an Azure region. And so we have the region, we create the VNet. Ideally, it's created in the region that's closest to the users that will consume the services offered. And it's important to allocate a large enough address space to accommodate for all the services that will be deployed and to allow for future growth. We then need to create subnets, as we mentioned, to deploy our workloads. And another concept that's important to mention is that of availability zones. And it is not required to specify an availability zone when deploying a workload. Unlike AWS, for example, availability zones, they are not tied to specific subnets. They are independent constructs, as you can see here. We have 2 availability zones in the same subnet. Each availability zone is a physically separated data center within the Azure region. So now that we have our subnets, we can start deploying our virtual machines in each subnet. We can have as many subnets as we have. And we can use network security groups at the subnet level to restrict traffic communication, or we can use them at the network interface level. Now, remember that by default, all virtual machines inside Azure have outbound internet connectivity, and they will use a random ephemeral IP address for this. So if we want a predictable and consistent IP address for outbound communication, we can associate a NAT gateway with the subnet that we want to allow for internet access. Now, if we want to inspect outbound internet connectivity through a firewall, then we can use a network virtual appliance from the Azure Marketplace in a separate subnet, and we can use user-defined routes in each subnet to send traffic through this virtual appliance. Now, because virtual appliances are virtual machine, if this virtual machine fails, it will result in an outage from all the workloads in the VNet that are using this appliance to access the internet. So it's important to deploy at least 2 virtual appliances behind a load balancer for high availability. And now to update the static routes to point to this load balancer behind them. It's also important to note that clustering is not supported in Azure, and users are responsible for making sure that all MVAs are properly configured. Another option, instead of using MVAs, is to use the native Azure Firewall, which is a highly available managed service. Now, if we want internet egress, we can either use public IP address as allocated to each virtual machine hosting service we want to expose to the internet, or we can place the virtual machines behind an external load balancer in Azure and associate the public IP in the load balancer. However, if it is desired to inspect traffic through a firewall, this can be MVAs, or we can use Azure Firewall. One thing to note in the architecture when we have MBAs behind load balancer is that the external load balancer and the internal load balancer, they don't share state. So it's very important to do source NAT of traffic coming from the internet in order to guarantee flow symmetry, that return flows from Azure to the internet flow through the same firewall that processes the inbound request from the internet. This is not a problem with Azure Firewall because Azure Firewall by default performs source NAT, so you don't have to configure that. But if you are using an MBA, you do have to. Another ingress design pattern is using a service that Azure launched at the end of 2021 called Gateway Load Balancer. And what this service allows is to transparently insert virtual appliances for internet traffic
destined
to a public load balancer or public IP address. The way this works is the workloads or the virtual machines that are offering the service, like web servers, for example, they're placed directly behind an external load balancer. And then a gateway load balancer is chained to this external or public load balancer. Now, the gateway load balancer and the MBAs, which is represented as subnet tree in this slide, they can be in the same VNet or they can be in a different VNet, and they can even be in a different subscription and AD tenant. So this allows us to insert virtual appliances as a service. Now, the other thing with the gateway load balancer is flow symmetry is guaranteed. Hence, it is not needed to perform source NAT anymore at the virtual appliances as we saw previously. So this allows us to preserve the original client IP address. Now, for web traffic, the recommendation is to use Azure Application Gateway if the services are localized in a single region. We can also attach web application firewall policies to application gateway to provide a layer of protection. Remember, application gateway by itself doesn't do anything to protect our workloads. It's just an application delivery controller. The other option is to use Azure Front Door if the services are distributed in different regions or our users are distributed in different regions. This is so that the traffic is ingested closest to the end users. Azure Front Door can provide capabilities like content caching, as well as TCP acceleration, which provides for the best experience for the users. Also remember that we can use web application firewall with Azure Front Door to protect our web workloads against exploits as well. For on-premises connectivity, we again can use either IPsec VPN over the internet, or we can use a dedicated circuit for express route. We can also integrate with SD-WAN appliances in the VNet. And really, this is no different than deploying firewalls, as we have previously discussed, meaning that in order to send traffic to those SD-WAN devices, we need to use static routes. And we need to use a load balancer for providing redundancy. Another option, though, is to use Azure Route Server instead. This eliminates the need for all the static routes. Now, expanding on the patterns, we have hub and spoke. And this is pretty much the recommended architecture from Azure because it allows for scalability and segmentation. And as we discussed earlier, in this architecture, we have a hub VNet that has all the common services. Most likely, these are networking and security services. And then we have VNets that have the workloads, and those VNets are connected to hub VNet via VNet peering. And if we want to use inspection between those VNets, remember that here VNet A and VNet B by default cannot communicate. We need some routing device in the hub VNet. In this case, it's Azure Firewall, but we need these static routes to send traffic to Azure Firewall in order to make this communication possible. Now, this architecture can be extended to multiple regions. In this case, the recommendation is to have one hub per region in order to avoid traffic going all the way to the remote hub and then coming back, because that can add a lot of latency. So pretty much in this scenario, every hub in every region would need an appliance that can perform routing. Again, in this case, it's Azure Firewall. And this increases complexity because now we also need route tables in the hub VNet, specifically where that routing device, again, Azure Firewall, is located, in order to be able to send traffic to the remote region. So you can see how as the number of regions and the scale of these hub and spoke topologies increase, the complexity and management overhead increases as well. In order to solve these challenges, Microsoft came up with a new service called Azure Virtual WAN in 2018. And what Azure Virtual WAN is, it is a global mesh of managed hub virtual networks that provides any-to-any connectivity across all entities connected to those hubs. These entities can be virtual networks, can be site-to-site VPN branches, can be express route branches. They can be remote users connected via point to site, and it can also be branches connected through SD-WAN devices. Now, because the hub is managed by Microsoft, customer workloads cannot be deployed in the hub. Instead, only services like express route gateways, site-to-site VPN gateways, point-to-site VPN gateways, some SD-WAN solutions, and Azure Firewall are the only things that can be created into these hubs. These hubs can be deployed in any Azure region, and then customers would deploy their workloads to a regular virtual network that they own and manage and resides in their own subscription. And then they would connect these virtual networks to the hub that's in the same region as the virtual network. All workloads across Azure and on-premises that are connected to any of the hubs in the same virtual WAN construct can communicate among themselves without the need to manually configure route tables. If traffic segregation is desired in this scenario, it can be achieved by either deploying Azure Firewall in the hub or by using a construct called custom route tables, which is specific to virtual WAN. And this can be thought of separate routing domains, much like VRFs in on-premises networking. However, address overlapping is not supported. So it's not a true VRF, it's just a routing domain. It's also important to note that neither Azure Firewall nor custom route tables can be used to restrict traffic between branches. It is only to restrict traffic between VNets or between VNets and branches, but not between branches. Azure Virtual WAN doesn't come without these challenges, however. For instance, only Azure Firewall and more recently, as of late 2021, FortiGate are the only firewalls that can be deployed in these hubs. It's possible to deploy other firewalls as virtual appliances in spoke virtual networks connected to this hub. There are actually a lot of limitations with this design. First one is that VNet to VNet traffic is not supported. If you need to inspect traffic between two VNets, you have to connect those VNets to the VNet where the NBA has been deployed. So pretty much you go back to the hub and spoke model. And of course, because of this, now you need to use static routes, user-defined routes in these VNets to send traffic to that NBA. So really the benefits that V1 offers, they go away if you want to use an NBA that's not FortiGate or Azure Firewall. If inspection between the virtual networks and the branches is required, the branches connected to V1 hub, using an MBA, you must use SourceNAT at the firewall. Otherwise, there are going to be routing loops in the hub, and this has to do with the way virtual WAN hub routing has been designed. Nothing can be done around that. And this will break communication. So again, like traffic between VNets and branches must be source NATed at that MBA. Again, this is only if you don't use Azure Firewall or FortiGate, which can be deployed in the hub natively. One more thing is that traffic between virtual machines or virtual networks connected to hubs in different regions cannot be inspected because asymmetric routing that happens with virtual WAN. So that's a problem. You cannot have inter-region traffic inspection. Another challenge with virtual WAN is that it is specific to Azure. And although it can be used to connect other clouds as if they were branches, either through Express Route or Direct Connect or Cloud Interconnect or via IPsec VPN tunnels, this results in a fractured control and data plane across all clouds because, of course, V1 can only be used inside Azure, and then you would need to use a different service in each other cloud provider. So you have disjointed networks and data and control planes. This increases operational complexity. Furthermore, Virtual WAN is offered as a black box, which means there's very limited troubleshooting and visibility exposed to the users. And although Virtual WAN attempts to reduce the complexity with managing and maintaining route tables, when custom route tables are used, the complexity increases as the number of routing domains and hubs increases, because custom route tables are local to a single hub, and each route table must be independently managed and configured. So we go again back to the problem to having to manage route tables. There are also some scalability limitations with V1. For example, a single hub only supports 2,000 VMs across all VNets that are connected to that hub. And because Virtual WAN uses VNet peering to connect the virtual networks to the hub, only 500 VNets can be connected to a hub, including remote hubs. The other thing is aggregate throughput among whole VNets connected to a hub is limited to 50 gigabits per second. However, this number is not available from the start. Initial throughput is much less than that, and it can actually take a couple of hours for the hub to scale out to those 50 gigabits per second. When express route branches are connected to a hub, the number of CIDRs across all VNets and branches cannot exceed 1,000 CIDRs. And again, this has to do with the limitation we mentioned before about express route not being able to receive more than 1,000 different CIDRs from Azure. Another service that Azure came up in late 2021 is Azure Network Manager. This service simplifies management of virtual networks at scale across subscriptions by grouping virtual networks into what's called network groups. This association of virtual networks to network groups can either be static by manually selecting which VNets belong to a network group, or dynamic by using attributes like VNet name, VNet ID, or tag. Security or connectivity configuration can be applied to a network group. Security configurations allow administrators to enforce rules across all network security groups associated with VNets that belong to a network group. And connectivity configurations simplify connectivity among VNets in a network group by choosing between hub and spoke or mesh topologies. And Azure takes care of setting up the peerings between VNets in the backend automatically in order to comply to the topology defined in the network group. There are still some challenges with Azure Network Manager, however. Although connectivity configuration simplifies the task of configuring VNet peering, it doesn't really help with service insertion and UDR management for steering traffic to a firewall. So if you want to inspect traffic between VNets in a hub and spoke topology, let's say, we still need to deal with configuring those static routes and UDRs. The other thing is that security configuration is limited to managing NSG rules only. That's what it helps with. It's for managing NSG rules at scale. Also, just like Virtual WAN, Network Manager is an Azure-specific service, so it cannot be used to manage constructs in other clouds. And although a certain degree of traffic segmentation can be achieved by grouping virtual networks in different network groups, the number of segments and the number of network groups increase. It also increases the management complexity because each one of these network groups must be managed and configured individually. Lastly, is Network Manager relies on VNet peering for the connectivity configurations. So because of this, we have the limitations of VNet peering. There's no visibility into traffic flowing between VNets, traffic flows unencrypted, and there is a limit of 500 VNet peerings. So that's it for Azure. Let's go on to GCP.